So we were looking at physical problems in Klein-Gordon field essentially, okay, with the Klein-Gordon equation and the solutions associated with it. Okay. So we were looking at putting potentials, constructing wave packets and putting potentials essentially. So and constructing wave packets, we said that you can always construct wave packets, but there will be problems with associated with wave packets essentially, because if you put in interactions essentially, as we will see later on, I have not shown you this thing essentially, as we will see later on, there could be problems associated with some funny behavior with the currents essentially constructed out of these wave packets. The reason is that the moment you put in the potential, as I said, that it will lead to interactions between the negative energy solutions and positive energy solutions, and they will lead to rapid oscillations, which has a German name which is called Zitterbewegung. Okay. And this was first observed by Schrodinger, of course, and this leads to problems in interpretations essentially. This leads to problems in interpretations. And then this is one thing which we can talk about wave packets. And the second thing essentially, before further proceeding, we were talking about solving potentials essentially, and we said that potentials which can be solved exactly in the Schrodinger equations need not be solved exactly in the Klein-Gordon field, and vice versa. There are of course exceptions. Okay. There are of course exceptions to this essentially, that there will be some cases in which they are exactly solved. So we will consider a step like potential essentially, we can call it an electrostatic potential also essentially, idealized with a sharp boundary which is idealized electrostatic potential. So this is the first scattering problem which we deal in quantum mechanics. In ordinary quantum mechanics, the first thing we do is take scattering across a step potential, and we will try to replicate this in the with the Klein-Gordon equation essentially. Now this leads to a paradox which is called the Klein paradox. Klein is essentially the same Klein as the Klein-Gordon equation essentially. So this is called the Klein paradox. Now Klein paradox in Klein-Gordon equation. Okay. So what we will consider is, so let us consider a potential as of this type. This is your region 1, this is region 2. Now this axis we can call it as z essentially, we can always call it x also, it is one dimensional problem, but for okay, but we can take it as z, and the potential has a height V0. Maybe I will plot it with another pen. Okay, this has a plot of V0. Now as in the standard case essentially, we will consider the situation in which there is a wave coming from the left. Okay, the wave is a wave coming from the left, but here we will choose the boundary condition, in the sense that there is a wave coming from the left, scatters of this potential in the okay, and then we will see the conditions, various conditions essentially. So the main condition we will choose is that because we have to choose some boundary condition here, in the sense that we will insist that the wave which is coming from the left, which we have given in this particular fashion, coming from negative z to the towards the origin and towards the positive z, okay, and positive z, should always has only positive energy solutions of the Klein-Gordon field essentially. So we are insisting that it has only positive energy solutions, and that is our initial condition. Okay, that is our initial condition. So we will say that because when we are in a relativistic framework, we will choose that A mu, you have to choose a potential A mu, okay. So A0 A bar, and we choose A bar is equal to 0, A0 is equal to V0 of say some z essentially of this wave function, okay. So this is the assumption we make, and then we will make, like in ordinary quantum mechanics, V0 of z is equal to 0 when z less than 0, when v is equal to V0 when z greater than 0, okay. Now how does the Klein-Gordon equation will look like? Essentially this will look like minus del T square phi plus del square phi minus m square phi is equal to 0 when z less than 0, because obviously the potential is 0. So it is just a free particle essentially, and whereas in when z greater than 0 essentially you will have I del T minus V0 whole square. Remember that it is only the time component gets modified, because we have chosen A0 essentially, as we have seen above. Essentially it is only the time component which gets modified, del square phi minus m square phi is equal to 0 for z greater than 0. So do you all agree with this essentially? I think, okay, it is a straightforward essentially. So what we are looking for now, we will look for solutions essentially of this Klein-Gordon field, okay. So what we are looking for are a positive incoming energy beam essentially, okay, positive energy. So it has solution, it is coming from incoming wave has so it is coming from z is equal to minus infinity to z is equal to plus infinity, is of the form, so e power minus I e t minus p z. It is one dimensional problem, so essentially I am saying, so phi, okay, phi is essentially of this particular fashion. So it has positive energy only. So I chose by initial condition that there is only one sign of the energy which is allowed for the positive energy essentially. So what we are looking for are solutions, okay, for z less than 0 essentially, or for z less than 0 you have phi less than 0 essentially is equal to e power minus I e t e power I p z plus real, one second, I will just, bracket should come, I p z plus r e power minus I p z for z less than 0. Now why this is the case essentially? Now e power IET essentially is the energy which is a free particle energy essentially. Then you have from front moving wave essentially moving towards the right, essentially wave moving towards the right, and you also have a wave which is reflected back essentially, exactly like in quantum mechanics. So here there we take coefficients A and B essentially, here the you directly write it in terms of a reflection coefficient. So R essentially I wrote it down in terms of the reflection coefficient R with a backward moving wave essentially or left moving wave essentially. for z less than 0. Now for z greater than 0, I only have one particular wave which is nothing but the transmitted wave, okay, which is given by e power I t. Okay. Okay. So instead of writing coefficients A and B, essentially I write down directly in terms of reflection and transmission coefficients essentially. So these are R and T are reflected and transmitted amplitudes, okay, okay. R and T are reflected and now what is P prime? P prime is the momenta in region 2. So in the momenta in the region 2 is the momenta in this particular case in the region 2 is where the potential is on essentially. Now I substitute these solutions and this will give me for z greater than 0 E square minus P square minus M square is equal to 0. So E is equal to plus P square plus M square for no, this is for z less than 0, sorry, because this is the incoming wave. Now this choice of plus here is by initial condition, okay, this is by initial condition. So I am choosing only one positive sign, okay. I can always choose my incoming wave, but I do not have a choice with my reflection and transmission coefficients essentially, transmitted waves essentially. Now let us look at the reflected and transmitted waves essentially. So I have E square for z greater than 0, I have E square plus V0 square minus 2 V0 minus P prime square minus M square is equal to 0. That means P prime is equal to both positive and negative E minus V0 whole square minus M square. So I have a choice in the momentum in the region 2. I have to consider both positive and negative energy, negative momenta essentially. So P prime, both the solutions should be considered essentially. Now for the case of the incoming wave, I can say that my incoming wave is only constructed out of a positive energy state essentially, but this sign here, the sign of this square root, you cannot fix it because you do not have any choice essentially, okay. What fixes it? What actually fixes it is you will have different cases, the strength of the potential if you want essentially, okay. So what happens is that if you plot the potential, okay, you will have several cases essentially. Let us look at it systematically. So So there is something called the strong potential region, where E it is plus MC square C is equal to 1 essentially, okay, plus MC square. Let us put C for not equal to for a change essentially, okay. This we will put it in another color essentially. C is not equal to 1, okay, okay. for a change, okay, just to see essentially. Then there is an energy E minus C square. These two are something called intermediate potential regions. And the third one is called weak potential regions. So how do I divide these three regions essentially? So weak potential region, okay, is when V0 is less than E, okay, minus M, E minus M. So this implies E minus V0 is greater than M, so that means P prime is real. Now remember this condition which we have seen here essentially, that P prime is equal to E minus V. So what is the comparable between V? So whether E minus V0 is greater than M square or less than M square is the condition what we are tracing at essentially. So it depends upon V is very small compared to E minus M. So V0 is very small compared to E minus M. So that is a very weak potential region. P prime is real, okay, and this line corresponds to E is equal E minus M, E is equal E minus M. This line corresponds to E plus M, this line corresponds to E, okay. This line corresponds to E plus M, this line corresponds, okay, we can remove the confusion essentially that, okay, E minus M, E plus M, okay, and this is E minus M and this is E plus M. Now the region which is when V0 is if the potential lies below this line, below V minus M essentially, and then that is called weak potential region. If the potential rise below E, that is, or E plus M, okay, okay, then it is called as intermediate potential region essentially. In this case essentially what happens is P prime is imaginary. So E minus modulus of E minus M is always less than M. So that means that P prime is purely imaginary, okay, it is purely imaginary. So and then there is the last region, E minus V0 is greater than M, that means P prime is real. Now you can, of course you can say that, okay, so M plays a crucial role essentially in distinguishing these three regions essentially, the mass of the particle, so and the potential also. So the mass of the, it is an interplay between the energy, potential and the mass of the particle essentially. So now whether the momentum in the region 2 is real or it is purely imaginary, it is depends upon the relative strengths of these three things essentially. In the weak potential region what we have seen is that, okay, that P prime is real essentially, so there are not oscillatory solutions essentially. Now but what we had to look at in the region of strong potential, say for example the kinetic energy E minus V0, okay, say for example modulus of E minus V0 because V0 is greater than E plus M, E minus V0 is greater than modulus of E minus V0 is greater positive. Okay. Now the kinetic potential in this case is here, the kinetic energy is negative, forbidden. This is forbidden classically essentially. Okay, maybe this is known essentially, and the group velocity is given by, in classical mechanics it is not allowed essentially, this such a situation is not allowed, but in quantum mechanics it is allowed essentially because you can have small. Okay. And then you have to look at the group velocity. Group velocity is given by P prime by E minus V0. So now that what we had to choose, the choice of P prime sign essentially is fixed here essentially. So P prime has to be, okay, negative in this case because E minus V0 is negative, and then if we have to choose negative such that the group velocity, okay, now should not come from z going to positive infinity essentially. Now the point is that the group velocity of the wave packet should not be coming from here essentially, should not be coming from this direction essentially. So what we are looking at is P prime is the region in this essentially. So you do not have any wave passing from here essentially. So what we have is a wave from here, so wave from here, you have a wave from here, but the wave should go here essentially. So there should be a wave which is going here essentially, there should not be a wave which is coming back from positive positive z essentially, z goes to positive infinity essentially. So we do not want anything coming from there. So we had to choose your group velocity such that P prime by E minus V0 should be positive, and so this automatically fixes your P prime to be negative, because you only have transmitted wave, because our initial condition tells you that you only have a initial wave, transmitted wave and reflected wave. There is no another barrier or something here such that it can have a transmitted another further transmissions essentially. With this, okay, this is purely focused for this thing, and so now imposing boundary conditions of continuity for phi and del z del phi at z is equal to 0 gives us e power minus et 1 plus r is equal to t e power minus psi et. This implies 1 plus r is equal to t, and with the derivative you have the other condition e power minus psi t ip 1 minus r is equal to ip prime t e power minus psi t implies 1 minus r is equal to p prime by p t, and so we can solve for r and t. Okay, we can solve using these two equations, we can solve for r and t, which gives you the conditions r is equal to p minus p prime p plus p prime, and t is equal to 2p by p plus p prime. Now what is the current? Now okay, we have got R and T essentially. Now that is not sufficient, we also have to calculate the currents essentially. So what is the positive current, and to calculate the transmission and reflection coefficients, we have to compute the currents essentially on both directions essentially. R and T are only the amplitudes, okay, amplitudes, reflection and transmission amplitudes. Okay. Now to calculate the coefficients, we have to calculate the currents essentially. The current we have seen, the Klein-Gordon current is equal to 1 by I to I phi star del phi minus phi del phi star. So the incident current J I, because only has positive energy, is P by M, and J in the incident current. Now let us calculate J in Z less for Z less than 0. So 1 by, so you can calculate this, and this will end up being okay, you can, I will just do one step essentially, e power minus I p z plus r star e power I p z I p e power I p z minus r e power minus I p z times minus e power e power I p z plus r e power minus I p z I p minus e power I p z plus r star e power I p z, then full brackets essentially 1 by 2 m essentially. This entire thing just simplifies to e power p m 1 minus mod r square. Similarly for z greater than 0, you end up having j greater than 0 is equal to p prime plus p prime star by 2m mod t square e power I p prime minus p prime star z. Okay. Now what you will see is that you have for j greater than 0 this thing very nicely given, whereas the greater than less than 0 is very nicely given in terms of p, but j greater than 0 has this complication that it has p primes and p prime stars essentially. Now but p prime can be both real and imaginary. So what happens? So p prime is equal to real. When it is real is p prime by m mod t whole square for p prime real, because for p prime real p prime is equal to p prime star. So this automatically is very simple to solve essentially, and for p prime is complex essentially or imaginary, this is 0 for p prime imaginary, then p prime is equal to minus p prime star essentially. Okay, so this will cancel off and everything, so this will goes to 0 essentially. So you have the cases where the potential, now remember that p prime is real when you have extremely weak potential or very strong potential, and p prime is imaginary for intermediate potentials. Okay. Now you put it back into calculating the transmission coefficients. is equal to j cap times j incident. So, this is given by two p prime plus p prime star by p prime plus p prime star plus p e power I p prime minus p prime star z. Similarly, you can calculate the reflection coefficient. Reflection coefficients, I will write it in terms of the curly r. Now, the difference between reflection coefficients and reflection amplitudes and this thing is, as I think you can understand, j incident minus j less, meaning less than 0 by j incident. So, that is equal to mod r square, it will end up being mod r square, that is equal to p minus p prime by p plus p prime whole square. Okay. So, these are the solutions we end up with. So, now we have to calculate, we have to see, make sense out of this thing. Now, we know that reflection coefficient, transmission coefficient plus reflection coefficient should be equivalent to 1, and if p prime is real for weak potentials, then T is equal to 4p p prime by p plus p prime whole square, and R is equal to p minus p prime by p plus p prime whole square, and you get T plus R is equal to 1. This is fine. For intermediate potentials, T is equal to 0, R is equal to 1, because we have seen the transmission is 1, T plus R is equal to 1. So, all fine, so far so good, but for strong potentials, as we have seen, p prime is real and negative. P prime is T and negative, then T is equal to minus 4p mod p prime by p minus mod p prime whole square, whereas R is equal to p plus mod p prime p minus mod p prime whole square. Now, this is a big issue because the transmission coefficient is negative and the reflection coefficient exceeds 1. So, you have some result which does not make sense. R greater than R here is the reflection coefficient, not the amplitude, and T is negative. So, in the limit, okay, so here in the, for the case of weak potentials, what we have seen is that P is positive, essentially P prime is positive, whereas for strong potentials P prime is real and negative, and then there is no other choice because we had to use the group from the group velocity arguments essentially. Okay. So, from these two arguments, when I actually calculate using the current, the incident current, and then I calculate the transmission and reflection coefficients essentially, I see that the case of strong potential leads to illogical reasons essentially. It leads to illogical reasons because we cannot understand scattering with negative transmission coefficients and reflection coefficients greater than 1. So you still can say that T plus R is still equal to 1, but with some unphysical T and R essentially, with unphysical T and R. So this paradox is called Klein's paradox, that if you do scattering in the presence of a strong potential, okay, we will see this in another way essentially with the Dirac theory. This recurs also in Dirac theory on any relativistic wave equation essentially, that if you have strong potentials essentially you will end up with nonsensical answers like the transmission coefficient is negative or the reflection coefficient is greater than 1, which you cannot have a proper interpretation. As we will see later on, once we understand the whole theory and various other aspects of antiparticle systems essentially, that we will see that this is because in the presence of strong potential you will create positive and negative energy pairs essentially, and this will create issues essentially, and this will change your transmission and reflection coefficients. So in the presence of strong potentials, because there is enough energy, potential energy to create positive and energy negative energy particle antiparticle pairs, this will spoil our way of calculating things by considering only starting with only positive energy. So if you, because we started the entire Klein paradox is because we started with saying that only okay, I throw out all the negative energy states and I only start with only positive energy state essentially, and assuming that there is only positive energy state, I do not care about the negative energy state. If I try to do potentials calculations like in non-relativistic quantum mechanics, we will end up having nonsensical results essentially. This is the main crux of the Klein paradox. Okay, we will discuss in little bit more before moving to Dirac theory in the next lecture. Okay, I will stop here. Thank you.